Hello again and welcome to my channel. We've looked at some passive components in the past, resistors and capacitors. And by passive it means that you don't use an electrical signal to switch them as you would with transistors and thyristors and things like that, which are active components. So the passive component we're going to look at today is going to be the diode. So what does a diode actually look like as a symbol? Well, the circuit symbol for a diode is that. So you can see it's an arrow on flat bit. And the actual diode component I've drawn there is basically a square with a line at one end. And what the line at one end dictates is that's the cathode end. So it's got an anode and a cathode. The anode is usually the positive side and the cathode is the negative side. So let's have a look what a diode does when you put it into a circuit. If we connect the diode into the circuit, so you can see that the cathode, we're going to connect it in here, so it'll be to the negative side of the battery, and the anode is going to be to the positive side. What's going to happen? Well, the light is going to light. Now, we call that situation forward bias, but if we connect it the other way around, so if we turn it now so that the cathode is facing towards the positive side and the anode is facing towards the negative side, now there is no light, nothing is happening. So how does it do that? There are no moving parts inside the diode. There's no moving parts or anything in here. So how does it do that? It's got to be something to do with the component's chemistry. So if we look at what we've just done as a circuit, so you've got the anode and the cathode, they're connected to the lamp. The cathode's connected to the negative and the anode is connected to the positive. That's forward bias. And so in reverse bias, the cathode is connected to the positive and the anode is connected to the negative, and that's reverse bias. And in reverse bias you get no current flow. You only get current flow in forward bias. Now when you're talking about conductors and insulators, we have materials that conduct electricity like steel, like copper, aluminium, and we have insulating materials like rubber, glass and wood. And there are a group of materials which is somewhere in the middle, and they are called semiconductors. And semiconductors are built around silicon. Now, the way the component, the diode, behaves is because of the makeup of the silicon atom. If you remember in previous tutorials, we've said that electrons flow, you get electricity flow because electrons jump from atom to atom, and electrons are called charge carriers. And if we look at the silicon atom, what we have is in the valency shell, if you remember, we call the outer shell of the atom the valency shell. So we've got the nucleus there. And in the valency shell, you have 1, 2, 3, 4 electrons. Now, with silicon, so the silicon atom wants 8 electrons in this shell. And in the valency shell, it's only got 4. And what it does, it gangs up with 4 silicon atoms around itself. And they share electrons. So these electrons will be shared, so they'll hop from that silicon atom to that silicon atom. And they'll hop from that one to that one, that one to that one, and that one to that one. It's called covalent bonding. So these electrons will be shared amongst the silicon atoms. Now, silicon is a poor conductor at sort of room temperatures, if you like, but there's enough energy to allow some free electrons and some electron movement, so you can get a tiny current through it. But we want more than that. So what we need to do is to add other materials to the silicon. Now this process is called doping, and that's an important one to remember. And doping means you'll add other atoms to it, and you can have aluminium, which is a trivalent material. So you can add, there are a number of different trivalent materials, one of them being aluminium. So you can add aluminium to it. You can add something like arsenic to it. And arsenic has 5 electrons in the outer shell. And so that's called a pentavalent material. Pent meaning 5. So we can dope the silicon with arsenic or with aluminium or with other trivalent and pentavalent materials to get the silicon to conduct better, to make the essentially a non-conductor, although it conducts a little bit, into a semiconductor material. And we can form P materials and N materials, and P materials have an excess of holes. As we said, when an electron moves, it leaves a hole behind it. So with a P-type material, you get an excess of holes. And with an N-type material, you get an excess of electrons. So the N-type material is a donor material because you're giving electrons to it. And then a P-type material is an acceptor because you're filling the excess of holes with electrons. So they are known as acceptor materials. So when we make a diode, then we get a P-type material and an N-type material. So that will be the P material. And here's an N-type material. And in the middle here, you get forming a junction. So it's a PN junction. So those two different types of dope materials go together to form the diode. So what I want to look at now is to look at the lattice work of the atoms in this, just to see how the charge carriers are moving. If we first of all look at an N-type material, so an N-type material, as we said, is pentavalent. You can see here 1, 2, 3, 4, 5. So we're looking at phosphorus in this case. Phosphorus is a pentavalent material and it's used as a doping material as well. So it's a donor material because it's got an excess electron. So what happens is you've got the phosphorus atom, and that's going to bond with 4 silicon atoms. So you can see the bond there, the bond there, the bond there, and the bond there. But now it's got an excess electron. So that frees up this electron for a bit of movement throughout the material. So you can start to see now how this material is becoming a semiconductor, because you've got this electron charge carrier, which is negative, electrons are negatively charged, N, to freely move about in the material if we put a voltage across it. If we look at the P-type material, now the P-type material we're going to look at here, the trivalent material here, is going to be boron. And boron is another material that's used for doping silicon to make these semiconductors. The P-type material, as we've said, is an acceptor material. So we can see now that the boron atom has got 3 electrons in its outside shell. So it bonds with a silicon atom there, a silicon atom there, and a silicon atom there. But wait, now it's only got 3. So this silicon here, those two are bonded, those electrons there. But what happens is this electron is going to jump over here for a period of time as well. So as we said, if an electron moves anywhere, it's going to leave a hole behind it. So the hole in this case is the charge carrier in the P-type material. So P-type material, the hole is the charge carrier. The N-type material, the electron is the charge carrier. So this is going to jump now back and forth here, leaving a hole, a positively charged hole, because the electrons are negative. So if an electron jumps out of there, then the balance is upset, and of course that's going to become positive. So positive holes. So the holes are going to move as the electrons jump around as well. So your hole is your charge carrier here, because it's being shared between silicon and the boron atom. So if we look at the action of the diode now, how it actually works, what we've done here is remove the silicon atoms and the dopant material atoms, the aluminium or boron or arsenic or whatever it is, and we just leave in the majority charge carriers. So here on the P side, you can see the red suites are representing the holes, and on the N side, the majority charge carriers are electrons, so they're the blue suites. So if you notice, in the middle, around the P junction, we have a layer where there are very, very few, or actually hardly any at all, majority charge carriers. So it's depleted of charge carriers. So this is called the depletion layer or the depletion zone. So there are no charge carriers in here because effectively they've migrated back into the material. And now that's at the point of manufacture. So now if we look at the diode in the reverse bias connection, so that means the negative of the power supply is connected to the anode, and the positive of the power supply is connected to the cathode. And what we find then is that the majority charge carriers move to the ends of the device, i.e. the ends, the negative electrons, are drawn towards the positive side of the supply because unlikes attract. The positive holes are attracted towards the negative of the power supply, the cell in this case. So you get a very wide depletion layer or very wide depletion zone. So there's no charge carriers in there. And so you get no current flow. That is acting as a valve now, preventing current flow. Okay, now if we look at the forward bias now, so the forward bias means the positive side is connected to the anode of the device and the negative side is connected to the cathode of the device. As we always know, cathode is negative, anode is positive. So that's forward bias. So in this scenario now, electrons are being injected by the power supply and they have movement in this direction. So these electrons now are all going forward here. And of course the holes now are attracted towards the negative side because holes are going to be what the electrons jump into. So effectively the holes are moving this way. So that's it. We have electron flow going that way, so we have a current. So we now have a current flow in forward bias on electron flow going that way around the circuit. And we have a very narrow, if not non-existent, depletion zone. So now, in this scenario, in forward bias, we have the current going around. So that's how we actually see the diode operating, with the current flow in forward bias and no current flow in reverse bias.